intersecting a cylinder and a plane. Can you find the area of the ellipse? So over here, the thing is, there is this cylinder, right? So basically, this is y coordinate axis. This is z coordinate. Okay, the one going front. So basically, this one is like z, and the one going up. This is actual x coordinate axis, right? So there's this cylinder. So basically, the circle y square plus z square is equals to 6. It doesn't depend on x, right? So no matter what x is, like it will always be a circle, right? So that's what this is a cylinder. And there's another plane. So this ellipse, it lies on a plane, right? So this lies on a plane. So to denote the plane, like I have made these little lines over here. So yeah, and this plane is given by the equation 5x minus 9y plus 3z is equals to 11, right? Now the intersection of the plane and the cylinder is giving us an ellipse, right? So this ellipse, the ellipse over here, we want to find the area, sorry, and we want to find the area of this ellipse, right? This ellipse. Okay, how would you find that? Now, like I didn't know this idea, so there's actually a pretty simple idea. Because of which I was pretty interested to make this video, and yeah, I think it will be helpful to you as well. So basically, if you project this ellipse onto like this flat plane over here, somewhere like there, right? So over here, this will just be a circle, right? If you project this to a flat plane, basically YZ axis at certain height, right? Then this will just be a circle, right? And if you're and like after we know that the projection is circle, and also it's easy to find the area of the projected circle, area of the projection which is circle. It's easy to find that area, right? So because the radius over here is just root 6, because this should be r square. So that means the area of projection will just be pi r square. So pi root 6 square, 6 pi, right? Now this can be used to find the area of the ellipse, right? And this is actually pretty interesting. Just like how, let's say if this line has length 3 and this is angle theta, then this projection has length 3 cos theta. Similarly, over here, if now this is looking a bit messier, let me just erase a few things before I draw it again, because otherwise it won't be clear, I think. Okay, so now similarly over here, so let's say if this ellipse makes some, okay, so this ellipse is basically has some tiltation, right? If this makes some angle theta, right, then the area of this circle over here will just be area of ellipse times cos theta. So it's because the circle is just the projected version of the ellipse, so it actually works. The same cos theta analogy works for area too, and that was pretty interesting for me. So we just need to find this angle theta, right? So for that, you can actually take the normal of this ellipse, which is basically normal of this plane, and also normal of this plane. So because this is in YZ coordinate axis, so basically this normal will just have like, okay, so we can actually get, okay, so basically because this is a YZ plane, the normal here for this circle should just be 1 comma 0 comma 0, right? So basically just in the x direction, I'm having 1 on all the other 0. I can have like anything in x direction, but all the other like zeros. That's what this normal is, right? Because there's nothing in y or z, but only in x for this normal. And for this normal, because this is normal to a plane, so I can just use these numbers 5 minus 9 3, and that will be the normal, right? That's how this plane is defined. Yeah, because this plane itself is defined as like this dot product with x y z is equals to 11. This is how you define equations of plane, right? Yeah. So now because we have those two normals, we can find cos theta. So let's say this normal is a vector, and if this normal is b vector, so we just want like the angle between these two normals, right? Because this angle will be equal to this angle. Because the reason is this thing is like perpendicular. Okay, the thing is there's theorem that the angle between two vectors is equal to the angle between the perpendiculars. So corresponding to this red line, this is perpendicular to it, and corresponding to this line, this is perpendicular to it. Let me do another color. Corresponding to this line, this is perpendicular to it, right? So over here, basically corresponding to um these two lines. So if there's angle between them is theta. Similarly, between their perpendiculars, the angles between their perpendiculars, the angles will also be theta. So using that theorem, it's just enough to find angle between these two normals. So if we know that, this cos theta will just be a vector dot b vector by magnitude of a, magnitude of b, right? And dot product is just 5 by magnitude of a is 81 990 plus 25 square root of 115, right? 81 990 plus 25 115, and another is just square root of 1, so this is 5 by square root of 115, right? So now the area of ellipse times cos theta should be area of circle. Area of circle, we already know that's just 6 pi, and this is 5 by square root of 115 times area of ellipse, and therefore we easily find that area of ellipse is actually 6 pi square root of 115 divided by 5 square units, and that's the area, guys. Yeah. Yeah. Okay, guys. So this is the area, and yeah, this was actually pretty interesting way, right? The fact that area could also project it. Actually, like the formula of flux will also involve these properties and things like that. But yeah, this was actually pretty interesting that you could actually do it not just for length but also for area. Hope you enjoyed the video. Thanks for watching, and I hope you enjoyed, and I look forward to seeing you in the upcoming videos too.